So in general, it is a little bit difficult to find a good system for working with specific infinite cardinalities. Which is to say, it's hard to have a system of numbers that correspond to the size of infinite sets. This is a little bit a thing that you can do, so you can look into it if you're curious. But for our purposes, there is one important one that we're going to talk about, which is called countable. So let's define this right now. So a set A is countable if the cardinality of A is less than or equal to the cardinality of the positive integers. So I don't know if I've used this little upper plus notation before, but this just means positive integers. And what is, let's think about this name for a second. Why are we calling this countable? You can think of an injection from A to the positive integers, which is what this means, remember? If you have an injection like this, you can think of it as labeling the elements of A by the positive integers, which is, you're essentially counting them. So this is why it's called countable. If you can write the elements down in a list, like the positive integers, then it is countable. And if you cannot do that, then it is not. So the opposite is called uncountable. And this is when the cardinality of A is strictly greater than the cardinality of the positive integers. So let's look at some familiar infinite sets. Let's start with the natural numbers. Remember, these are non-negative integers. Now, this is already starting to be an example of some strange ways that infinite sets can behave. Because you can think of this as positive integers, except that you've added another element. And for a finite set, this would change the cardinality. But for infinite sets, what you can do is just change your labeling so that this maps to 1, this maps to 2, this maps to 3, maps to 4, etc. And you can see that this rule gives an injection, and in fact a bijection, between the natural numbers and the positive integers. So the cardinality of the natural numbers is the cardinality of the integers, the positive integers, and it's countable. Or let me say, so there's a little bit of abusive language that goes on around these things. Technically, countable refers to any set that is no larger than the positive integers. But often it is used to mean a set that is infinite and the same cardinality as the positive integers. So if you want to be precise and specify that it's infinite, you can say countably infinite. Or you can say just countable. Because, this is first of all true, but second of all, you sometimes abuse language to imply that it's infinite when you say countable. question in the chat. Answered. Solid. Let's get another one. Or actually, let me point out a general rule that we can conclude from this. So we haven't proven this, but you can see, hopefully, from this example how you would prove this. This shows if A is countable and B is finite, then A union B is again countable. All right, so let's have another example. So how about full integers? Now, the natural numbers were easier because the positive integers are sort of infinite in one direction as you increase in number. And the natural numbers are sort of infinite in one direction as well. So we saw that we just had to shift the labels over and we could count them. But the integers are infinite in both directions. So if you try to do something like this, and then keep going in this direction, somehow no amount of shift to the left is going to make this a bijection. But as a general rule of mathematical thinking, just because you did not come up with an example does not mean that an example does not exist. It may mean that you just need to be a little bit more clever. So here's something that you can do. You can turn a one-sided thing into a two-sided thing by sort of jumping back and forth. So here, let's define a map from z to z plus. I'm writing this a little bit informally, but let's do it like this. So 0 is going to map to 1, and then 1 is going to map to 2, and then we're going to go onto this side, maps to 3, this side maps to 4, this side maps to 5, this maps to 6, and so on. And you can see that as you continue this process, it will go on forever in both directions. And so you actually get a bijection between the positive integers, which are sort of infinite in one direction, and the full integers, which are sort of infinite in both directions. So already this might seem a little counterintuitive. But what we have shown is that the cardinality of the integers is equal to the cardinality of the positive integers. And again, it's countable. And can we conclude any general rules from this? What this is kind of suggesting, or what you could maybe prove inspired by this example, in fact, even if you have two sets that are countably infinite, their union is still countably infinite. So you're starting to get the idea that you can do kind of a lot without changing the cardinality of these sets. It's a little bit difficult to produce a set that is uncountable. But let's keep trying. Next example. The rational numbers. So these are not only infinite in two directions, but they are also infinitely dense in some sense. So you have the integers like this, which go on in both directions, but you also have fractions, and you have infinitely many fractions between any two integers. So is there any hope that we can make this thing countable? Can we put this in bijection with the positive integers? And again, it turns out that we're in the same situation where even though it's not obvious from writing it like this, it turns out that actually we can. We just have to think about it a little bit differently. And it's another case of sort of writing things down in a more convenient way so that there is a natural path to count them. So I'm going to be a little bit informal and just write down the positive rational numbers, but I hope that you will be able to see how you could do it with all rational numbers instead. The idea is very much the same. So think about it like this. Let's write them down in a grid. So we can get every rational number as a fraction of integers. And if we write down a two-dimensional grid like this, where in this direction we increase the numerator, and in this direction we increase the denominator, and then we just fill it in, etc. So in this infinite grid, we have written down all the positive rational numbers. And then we can count them like so. This is number 1. This is number 2. This is number 3. This is number 4. So basically we're going to go through the grid in this kind of pattern. And you can see that it'll fill up the whole grid in a single line. And this is how we will count them. And if you want to be precise, you can skip over things that you already counted. So we already got 1. 2 over 2 is equal to 1. So this thing is number 5. Then this is number 6. This is number 7. This is number 8. This is number 9, etc. So by writing in this different way, we have shown the cardinality of the rational numbers is actually equal to the cardinality of the positive integers. And when I first saw this, I was very surprised. To me, this is very, very counterintuitive. It's a really nice example of the strange things that happen when you think about the sizes of infinite sets. And again, we can draw sort of a general conclusion from this example. So not only two countably infinite sets, but if you have a countably infinite collection of countably infinite sets, then the union is still countable. And in fact, if you wanted to, you could also think of this as a Cartesian product, because each rational number is essentially an ordered pair of integers. So that shows that, you know, the Cartesian product of two countable sets is still countable. Although maybe I'm going to make that a practice problem as well. I may have put that or not, I forget, but that's a good practice problem to show that. So we are getting the sense now that it is really quite hard to write down an uncountable set. Even taking a countable union of countable sets is still countable. So we'll have to do something even more than that.